The universe is not expanding into anything, and that single statement breaks most human brains the moment they hear it. We have been conditioned our entire lives to understand expansion as something moving outward into space that already exists. A balloon inflates into the room around it. A city expands into the surrounding countryside. An explosion hurls debris into the air that was already there waiting to receive it. But the expansion of the universe follows none of these rules. It defies every intuition we have developed since childhood. The universe is expanding, yes. Scientists have measured this expansion with extraordinary precision across nearly a century of observations. Galaxies billions of light years away are racing away from us at velocities that would make any science fiction writer envious. The fabric of reality itself is stretching like an endless sheet being pulled in every direction simultaneously. Yet there is no void waiting outside to receive this growth. There is no empty container the cosmos is filling. There is no boundary being pushed outward. The expansion is happening within the universe, between everything that exists, creating more space where space already was. This is not just a difficult concept. It represents one of the most profound realizations humanity has ever achieved about the nature of existence itself. For most of recorded history, humans looked up at the night sky and assumed it was eternal and unchanging. The stars moved in their predictable patterns. The constellations your ancestors recognized are the same ones you can trace tonight. Everything seemed fixed, permanent, a cosmic clock that had always ticked and always would. Then, less than 100 years ago, we discovered something that shattered that comfortable illusion forever. The universe had a beginning. It has been changing ever since that beginning, and its fate remains an open question that keeps some of the brightest minds on Earth awake at night. To understand how the universe expands without expanding into anything, we need to journey through nearly a century of astronomical discovery. We need to watch galaxies receding from us at impossible speeds. We need to detect the faint afterglow of creation itself, still whispering across the cosmos. We need to confront the terrifying reality of dark energy, a mysterious force that makes up 68% of everything that exists, yet remains almost completely unknown. We need to wrestle with a crisis unfolding right now in the world of cosmology, where two of our most precise measurements of how fast the universe is expanding disagree with each other in ways that should be impossible. And ultimately, we need to peer forward into a future so distant that numbers lose their meaning, where the expansion we study today will have consequences that reshape reality itself. This is a story about everything, about the space between galaxies and the space between atoms, about the moment the cosmos was born and the endless dark that may await it, about what it means to exist in a universe that began somewhere but has no edge, that started sometime but stretches infinitely in space. If you have ever looked up at the stars and wondered what lies beyond them, the answer is more stars, and beyond those more still. Not because there is no edge in some simple sense, but because the very concept of an edge does not apply to the universe as we understand it. This is perhaps the most counterintuitive idea in all of science. We are about to explore why it is also almost certainly true. Consider for a moment what it means that you exist at this particular moment in cosmic history. The universe is roughly 13.8 billion years old. Humans have existed for perhaps 300,000 years. Written history spans about 5,000 years. The scientific understanding that the universe even had a history, that it was not eternal and unchanging, emerged less than a century ago. You live in an extraordinarily narrow window of time during which humanity first became capable of comprehending the cosmic story, while also being embedded within a universe that still contains visible evidence of that story. A civilization arising trillions of years from now would see a fundamentally different cosmos, one that would hide almost all traces of the explosive birth we can still detect. You exist at precisely the right moment to witness the universe revealing its own history. This is not a privilege we should take lightly. Every telescope observation, every satellite measurement, every theoretical calculation adds another piece to a puzzle that was invisible to every human who lived before the 20th century. Your ancestors looked at the same stars you see tonight, but they could not know those stars were suns like ours. They could not know those faint smudges of light were entire galaxies containing hundreds of billions of stars. They could not know the universe was expanding, accelerating, evolving toward a distant fate of cold darkness. You know these things because you inherited the accumulated discoveries of generations of scientists who asked questions and refused to accept easy answers. That knowledge is precious and hard-won. The story we are about to explore is their story as much as it is the universe's story. It is a tale of unexpected observations, overturned assumptions, confirmed predictions, and remaining mysteries. It is a tale that begins with a single question asked by astronomers nearly a century ago, and leads to a crisis unfolding in physics laboratories and observatories right now. It is a tale that stretches from the first fraction of a second after creation to a future so distant that time itself may lose meaning. If you're ready to see reality differently, hit that like button and subscribe. The universe is about to get very strange. We begin. In 1923, a young astronomer named Edwin Hubble was working at Mount Wilson Observatory in California, peering through what was then the most powerful telescope on Earth. The 100-inch Hooker telescope had been operational for only 6 years, but it was already revolutionizing our understanding of the cosmos. Hubble was studying what astronomers of the time called spiral nebulae, mysterious pinwheel-shaped clouds of light scattered across the sky. Most scientists believed these nebulae were clouds of gas within our own Milky Way galaxy. The prevailing view held that the Milky Way was essentially the entire universe, a vast island of several 100 billion stars surrounded by infinite emptiness. Hubble suspected something else entirely. He was searching the Andromeda Nebula for a particular type of star called a Cepheid variable. These stars pulse with a regular rhythm, brightening and dimming over periods of days or weeks. What makes Cepheids special is that their pulsation period is directly related to their intrinsic brightness. A Cepheid that pulses slowly is genuinely brighter than one that pulses quickly. This relationship, discovered by astronomer Henrietta Swan-Leavitt in 1908, meant that if you could identify a Cepheid and measure how long its pulse took, you could calculate how bright it truly was, compare that to how bright it appeared, and you could determine how far away it must be. On the night of October 1623, Hubble photographed Andromeda and noticed what he initially thought was a nova, an exploding star. He marked it with an N on his photographic plate. But as he continued observing over subsequent nights, he realized the star was not exploding. It was pulsing. He crossed out the N and wrote VAR, for variable, with an exclamation mark. He had found a Cepheid in Andromeda. When he calculated the distance to that Cepheid, the number was staggering. The Andromeda Nebula was not a cloud within our galaxy. It was approximately 1 million light-years away by Hubble's initial calculation, far beyond the known boundaries of the Milky Way. Modern measurements have since revised this distance to about 2.5 million light-years, as Hubble's distance scale contained systematic errors that were only corrected decades later. But even his original estimate was revolutionary. Andromeda was not a nebula at all. It was an entire galaxy, a separate island universe containing hundreds of billions of stars existing independently of our own cosmic home. The Milky Way was not the universe. It was merely one galaxy among what would soon be revealed as billions. This discovery alone would have cemented Hubble's place in the history of science. But he was not finished. Over the following years, Hubble and his assistant Milton Humason continued measuring distances to these newly recognized galaxies. They also measured something else, the light those galaxies were emitting. Specifically, they examined how that light had been shifted along the electromagnetic spectrum. When an object moves toward you, its light waves get compressed, shifting toward the blue end of the spectrum. When an object moves away, its light waves get stretched, shifting toward the red end. This phenomenon, called redshift, had been measured for some nebula years earlier by astronomer Vesto Slipher. What Hubble and Humason discovered when they combined redshift measurements with distance estimates was nothing short of astonishing. Slipher's contribution to this story is often overlooked, but was absolutely crucial. Working at Lowell Observatory in Arizona starting in 1912, he had been systematically measuring the spectra of spiral nebulae. By 1917, he had found that most showed significant redshifts, indicating they were moving away from Earth at substantial velocities. The speeds were enormous, hundreds and even thousands of kilometers per second, far faster than anything else known in astronomy at the time. At the time, nobody knew what to make of these velocities. Were these objects somehow being flung out of our galaxy? Were they something else entirely? Slipher presented his velocity measurements to astronomical conferences where they created a sensation. But without knowing the distances to these objects, the implications remained unclear. It took Hubble's distance measurements to reveal the pattern hiding in Slipher's velocity data. Nearly every galaxy they observed showed redshift. The galaxies were all moving away from us. Furthermore, the relationship between distance and velocity was remarkably consistent. A galaxy twice as far away was moving away twice as fast. A galaxy 3 times as far was receding at triple the speed. This was not random motion. This was a pattern, a law. In 1929, Hubble published his findings. The velocity of a galaxy, he demonstrated, was proportional to its distance from Earth. This relationship would become known as Hubble's law, though the theoretical groundwork had actually been laid by Belgian astronomer Georges Lemaitre 2 years earlier. The implications were immediate and profound. If galaxies everywhere were moving away from us, and if farther galaxies were moving faster, then running the clock backward meant everything was once closer together, much closer. Perhaps at some point in the distant past, everything had been concentrated in a single point. The universe had a beginning, it had been expanding ever since. And we were watching that expansion unfold in real time. This was a philosophical earthquake as much as a scientific discovery. For millennia, most human cultures had assumed the universe was eternal or had been created in its current form at some definite moment by divine action. The idea that the cosmos had a natural history, that it evolved from a radically different state billions of years ago, challenged deep assumptions about reality. Lemaitre, who was both a physicist and a Catholic priest, proposed that the universe had begun as a primeval atom, an initial singularity that contained all matter and energy compressed to unimaginable density. This idea would later be developed into what we now call the Big Bang theory, though that name would not be coined until 1949. Some scientists resisted the implications. They found the notion of a cosmic beginning uncomfortable, perhaps because it seemed too close to religious creation narratives. Fred Hoyle, one of the most prominent astronomers of the mid-20th century, championed an alternative called the steady-state theory. In this model, the universe had no beginning and would have no end. It was eternal and essentially unchanging on large scales. As galaxies moved apart due to expansion, new matter continuously appeared in the gaps, maintaining a constant average density forever. The steady-state theory was elegant and avoided the troubling question of what came before the beginning, but observations would eventually prove it wrong. The first measurements Hubble made suggested the universe was expanding at about 500 kilometers per second for every megaparsec of distance. A megaparsec is about 3.26 million light-years. This meant that a galaxy 3.26 million light-years away was receding at 500 kilometers per second, while a galaxy 6.52 million light-years away was moving at 1,000 kilometers per second. This rate, now called the Hubble constant, has been refined dramatically over the decades. Modern measurements place it around 70 kilometers per second per megaparsec. The original estimate was too high by a factor of nearly 7, mainly because the distances to galaxies were being underestimated. The error in Hubble's original measurement had significant consequences for understanding cosmic history. A higher expansion rate implied a younger universe. With a Hubble constant of 500, the universe would have been only about 2 billion years old. But geologists had already determined that Earth itself was older than that based on radioactive dating of rocks. This created an embarrassing situation. The universe seemed younger than some of the objects within it. Only when astronomers realized that Hubble's distances were systematically too low did the problem resolve itself. With the corrected expansion rate, the universe turned out to be much older than Earth, as it should be. But the fundamental discovery was correct. The universe is expanding. This expansion is not galaxies flying outward through existing space like shrapnel from an explosion. Instead, it is space itself stretching, carrying galaxies along with it, like dots on the surface of an inflating balloon. The distinction matters enormously because it changes what we mean when we ask where the universe is expanding into. Picture a balloon with dots drawn on its surface. As you inflate the balloon, every dot moves away from every other dot. No dot is at the center of the expansion. From the perspective of any individual dot, all the other dots appear to be receding. The dots near the original one move slowly, the dots on the opposite side of the balloon move rapidly, and the dots are not actually moving through the balloon's surface at all. The surface itself is stretching, and the dots are simply embedded within it, being carried along by the expansion. This balloon analogy is imperfect, as all the analogies for cosmic expansion are, but it captures something essential about what the universe is doing. The galaxies are not racing through space away from a central explosion point. Space itself is expanding everywhere at once. New space is being created between every point in the universe simultaneously. The farther apart 2 points are, the more intervening space exists between them, and thus the more new space gets created per unit time. This is why distant galaxies appear to recede faster than nearby ones. It is not that they are moving through space more quickly, it is that more space is being created between us and them. To make this concrete, consider 2 galaxies separated by 1 billion light-years today. If space expands by 1% over some period of time, 10 million light-years of new space appears between those galaxies. But consider 2 galaxies separated by 2 billion light-years. The same 1% expansion creates 20 million light-years of new space. From our perspective, the more distant galaxy appears to be receding twice as fast, even though both galaxies are simply sitting still within their local patches of space. The expansion is happening everywhere uniformly, but its accumulated effect is proportional to distance. The numbers involved are staggering when you actually calculate them. At the current expansion rate of about 70 km per second per megaparsec, galaxy 1 megaparsec away, about 3.26 million light-years, is receding at 70 km per second. That might not sound like much, but a galaxy 100 megaparsecs away is receding at 7,000 km per second. A galaxy 1,000 megaparsecs away recedes at 70,000 km per second, which is nearly a quarter of the speed of light. The expansion velocity grows without limit as you consider more and more distant objects. This leads to a remarkable and troubling consequence. If you consider galaxies sufficiently far away, the rate at which new space is created between us and them exceeds the speed of light. This is not a violation of special relativity, which states that nothing can travel through space faster than light. The galaxies are not moving through space at superluminal velocities. Space itself is expanding, and there is no speed limit on how fast space can grow. Light travelling from those distant galaxies toward Earth is like a swimmer trying to cross a river that is widening faster than they can swim. No matter how hard they try, they will never reach the opposite shore. This distinction between movement through space and expansion of space is crucial and often misunderstood. When you drive a car at 60 miles per hour, you are moving through space that already exists. Your velocity is limited by the speed of light according to special relativity, but when space itself expands, nothing is moving through space at all. The galaxies are stationary within their local regions of space. It is the space between them that is growing. This growth has no speed limit. It is not motion in the usual sense. Consider an analogy. Imagine you are standing still on an infinite rubber sheet that is being stretched in all directions. You are not moving relative to your local patch of rubber. Neither is anyone else standing on the sheet. But the distances between all of you are increasing because the sheet itself is getting larger. A person standing close to you might drift away slowly. A person starting farther away drifts away faster because more rubber exists between you to be stretched. At some sufficiently great distance, a person is drifting away faster than you could ever walk toward them, even if you could walk at the speed of light. This is the situation with cosmic expansion. This defines what cosmologists call the observable universe. Beyond a certain distance, light emitted even at the beginning of cosmic history has not had time to reach us. Beyond an even greater distance, light emitted now will never reach us because expansion is too rapid. These horizons are not physical barriers. They are consequences of the finite speed of light and the relentless expansion of space. The universe may extend far beyond what we can observe, perhaps infinitely, but we can never see or detect or interact with those distant regions. They are causally disconnected from us. The observable universe forms a sphere centered on Earth, not because Earth is special, but because we are the observers making the measurement. Every location in the universe has its own observable universe, a sphere of the same size centered on that location. Your observable universe and the observable universe of someone in a distant galaxy overlap substantially but are not identical. A galaxy near the edge of your observable universe might be well within the central region of someone else's observable universe. They can see objects you will never see. You can see objects they will never see. But if you could somehow travel to that distant galaxy, instantaneously, you would not find a fundamentally different universe. You would find the same laws of physics, the same types of stars and galaxies, the same cosmic expansion happening all around you. The radius of our observable universe is at about 46.5 billion light-years, giving it a diameter of roughly 93 billion light-years. This might seem impossible since the universe is only 13.8 billion years old. How can we see objects 46 billion light-years away if light from them has not had enough time to reach us? The answer lies in the expansion itself. The light we receive from the most distant objects began its journey when those objects were much closer to us. As the light travelled through expanding space, the objects continued receding. By the time the light arrives, the objects are far more distant than the distance the light actually covered. The objects at the edge of our observable universe emitted their light 13.8 billion years ago, but they are now 46 billion light-years away because space has been stretching while the light travelled. Think of it this way. When that ancient light left a distant proto-galaxy, 13.8 billion years ago, that galaxy was perhaps only a few hundred million light-years from the location where the Milky Way would eventually form. As the light travelled through space, space itself was expanding behind it, beside it, and in front of it. The light was swimming upstream against a current of expanding space. Meanwhile, the source galaxy was being carried farther and farther away by the cosmic expansion. After 13.8 billion years of travel, the light finally reaches our telescopes. We see the galaxy as it was 13.8 billion years ago, but by now, that galaxy is 46 billion light-years distant. If we could somehow freeze time and measure its current distance, we would find it unimaginably far away. Beyond the observable universe lies everything we cannot see. There may be more galaxies, more stars, more planets, perhaps even other intelligent beings asking the same questions we ask, but we have no way of knowing. They are forever beyond our cosmic horizon, as inaccessible to us as if they did not exist at all. The total size of the universe is unknown and may be infinite. Observations suggest the universe is geometrically flat on the largest scales, consistent with infinite extent. If so, our observable universe is merely a tiny bubble within an infinite cosmos, and our horizon is the limit of our vision, not the limit of reality. Some cosmologists have attempted to place lower bounds on the total size of the universe by searching for repeating patterns in the cosmic microwave background that would indicate space curves back on itself. No such patterns have been found, suggesting that if the universe is finite, it is at least 250 times larger than the observable portion. But this is merely a lower bound. The true size could be vastly larger, or literally infinite. This leads to the profound and mind-bending truth that the universe is not expanding into anything. The balloon analogy breaks down here because in reality, there is no room that the balloon is inflating into. There is no outside to the universe. The universe contains everything that exists, including space and time themselves. It did not expand into pre-existing empty void because before the universe, there was no space for emptiness to occupy. There was no before because time itself began with the expansion. This is where human intuition simply fails. We are creatures of three-dimensional space. We experience time flowing in one direction. Every expansion we have ever witnessed has been an object moving into space that was already there. The idea that space itself can grow, that more space can simply appear where none was before, that this can happen without pushing into anything, contradicts every daily experience we have ever had. Consider what it means to ask where the edge of the universe is. If the universe has an edge, what would be beyond it? Nothing? But nothing is not a thing. There cannot be a region of nothing because a region is a spatial concept and space is part of the universe. Any region you could point to, any location you could specify, any coordinates you could write down, all of these are by definition within the universe. The question of what lies outside is not answerable because it assumes concepts that do not apply. Some people try to imagine a void, an empty space waiting outside the universe for the expansion to fill. But this misunderstands what nothing means. A void is still a spatial concept. It has extent, location, perhaps dimensions. It is something, not nothing. True nothing is not empty space. True nothing is the absence of space altogether, the absence of time, the absence of any framework within which existence could even be defined. This is almost impossible to imagine because our minds require frameworks. We cannot conceptualize a state where frameworks do not exist. Another way to think about this involves topology, the mathematical study of shapes and spaces. The surface of a sphere has finite area but no edge. An ant walking on the surface of a ball could walk forever without encountering a boundary. The surface curves back on itself. A two-dimensional creature living on that surface might not even realize it is curved. They might think they live on an infinite flat plane. Only by making careful measurements, like checking where the parallel lines eventually meet, could they discover the curvature. The universe might have similar properties in 3 dimensions. It could be finite in volume but without edges, curving back on itself in ways that are difficult to visualize but mathematically coherent. Or it could be truly infinite, extending forever in every direction. Current observations are consistent with the universe being flat and possibly infinite, but we cannot measure beyond our cosmic horizon, so we cannot be certain. Yet this is precisely what the mathematics of general relativity predicts, and it is precisely what nearly a century of observations confirm. Albert Einstein published his theory of general relativity in 1915, 4 years before Hubble's observations. Within this framework, space and time are not a fixed stage upon which the cosmic drama unfolds. They are dynamic participants in the physics, capable of curving, stretching, and warping in response to matter and energy. The equations of general relativity describe a universe that must be either expanding or contracting. A static universe, Einstein initially believed, was possible only if you added a special term to the equations, a cosmological constant that would counterbalance gravity and hold everything in place. Einstein's general relativity revolutionized our understanding of gravity. Newton had described gravity as a force acting instantaneously across space, pulling masses toward each other through some mysterious action at a distance. Einstein reimagined gravity as geometry. Mass and energy curve the fabric of spacetime, and objects moving through curved spacetime follow paths that appear curved from our perspective. What we experience as gravitational attraction is actually the tendency of objects to follow the straightest possible paths through warped geometry. The sun, for example, does not reach out and pull Earth toward it through some invisible force. Instead, the sun's mass curves the spacetime around it, and Earth follows a curved path through that warped geometry. From Earth's perspective, this curved path appears as an orbit around the sun. The mathematics of general relativity predicted this orbital motion with exquisite precision, matching observations better than Newton's theory ever could. The equations also predicted something else: a universe in motion. When Einstein applied his equations to the cosmos as a whole, he found that a static universe was unstable. Any initial state would either expand or contract. Disturbed even slightly, a static universe would either collapse inward under its own gravity or begin expanding outward. There was no stable equilibrium. This result troubled Einstein. Like most scientists of his era, he believed the universe was eternal and unchanging. The idea that it might have a beginning or might be evolving seemed philosophically unsettling. To avoid this conclusion, Einstein introduced his cosmological constant, a term representing a kind of cosmic repulsion that would exactly balance gravitational attraction. With this addition, his equations permitted a static universe. When Hubble's observations revealed the universe was expanding, Einstein reportedly called his cosmological constant his greatest blunder. He had the mathematical framework to predict cosmic expansion years before it was observed, but his intuition that the universe should be static led him to modify his equations unnecessarily. The irony is that the cosmological constant would return decades later as the leading explanation for dark energy, the mysterious force accelerating cosmic expansion. The mathematics that describe how space expands come from what physicists call the Friedmann-Lemaitre-Roberts Walker metric, named after 4 scientists who contributed to its development. These equations relate the geometry of space to its contents. Matter and energy curve space. In a universe filled with matter, space tends to contract under gravitational attraction. But if the initial conditions include rapid expansion, that expansion can continue against gravity's pull, gradually slowing over time. This was the picture of cosmic expansion that dominated for most of the 20th century. The universe was expanding, yes, but gravity was acting as a brake. Eventually, depending on how much matter the universe contained, the expansion might slow to a halt, reverse and end in a cosmic collapse. Or the expansion might continue forever, gradually approaching a standstill but never quite reaching it. This picture changed dramatically in 1998 when two independent teams of astronomers discovered something that shook cosmology to its foundations. The expansion was not slowing down, it was speeding up. Before we can understand how the universe expands today, and why that expansion is accelerating, we need to journey back to the very beginning. Not to the moment of the Big Bang itself, which remains shrouded in physics we do not fully understand, but to the first fractions of a second afterward, when the universe was an unimaginably hot, dense sea of energy and nascent particles. The term Big Bang is actually something of a misnomer, coined mockingly by astronomer Fred Hoyle, who preferred a competing theory called the steady-state model. The name stuck despite Hoyle's skepticism, but it creates a misleading image. Most people hear Big Bang and picture an explosion, debris flying outward from a central point into surrounding space. This is precisely the wrong image. The Big Bang was not an explosion in space, it was an explosion of space. Every point in the universe today can trace its origin back to the Big Bang, because the Big Bang happened everywhere simultaneously. There was no center, no surrounding void, no before. Understanding why there was no before requires grappling with one of the most counterintuitive aspects of modern physics. In Einstein's general relativity, space and time are not separate entities but components of a unified spacetime. The geometry of spacetime is determined by the matter and energy it contains. Near massive objects, spacetime curves, which we experience as gravity. In the early universe, when densities and temperatures approached infinity, spacetime itself was in an extreme state that our current physics cannot fully describe. The concept of time depends on the structure of spacetime. In the first fraction of a second after whatever initiated cosmic history, time as we understand it may not have existed in any meaningful sense. Asking what happened before the Big Bang may be like asking what is north of the North Pole. The question assumes a framework that does not apply. North is a direction defined on the surface of Earth. At the North Pole, all directions point south. There is no north of north. Similarly, time is a dimension of the spacetime that emerged with the Big Bang. There may be no before the beginning. This does not mean the question of what caused the Big Bang is meaningless. It means we need different conceptual tools to approach it. Some physicists speculate about quantum fluctuations in a pre-existing quantum vacuum that might have spawned our universe. Others propose multiverses, collections of universes where new Big Bangs occur continuously, each creating its own space-time bubble. Still others suggest that our Big Bang might have emerged from the collapse of matter in a previous universe, with space-time itself being recycled through cosmic cycles. These ideas are speculative and currently untestable, but they represent attempts to push past the limitations of our current understanding. According to our best current models, approximately 13.8 billion years ago, the universe existed in a state of almost unimaginable density and temperature. The entire observable universe, everything we can see or could ever theoretically detect, was compressed into a region far smaller than an atom. Physics as we know it cannot describe conditions this extreme. The laws of gravity and quantum mechanics likely merge into some unknown unified theory at these scales, a theory we have not yet discovered. We call this unknown epoch the Planck era, named after physicist Max Planck, who developed the fundamental constants that set the scales of quantum mechanics. During the Planck era, which lasted until approximately 10 to the negative 43 seconds after the beginning, the four fundamental forces of nature may have been unified into a single force: gravity, electromagnetism, and the strong and weak nuclear forces all behaved as aspects of a single unified interaction. As the universe expanded and cooled, these forces separated out one by one, like different substances crystallizing out of a cooling solution. The separation of forces followed a specific sequence determined by the decreasing temperature. First, gravity separated from the other three forces at the end of the Planck era. Then, at about 10 to the negative 36 seconds, the strong nuclear force separated from the still unified electroweak force. This separation may have triggered cosmic inflation. Finally, at about 10 to the negative 12 seconds, the weak nuclear force and electromagnetism separated, leaving the four distinct forces we observe today. Each force separation released enormous energy as the universe settled into new, lower energy configurations. The grand unification transition that separated the strong force may have released the energy that drove inflation. the electroweak transition left behind a sea of particles whose interactions would shape the universe's subsequent evolution. What we can say with confidence is that the universe expanded rapidly from this initial state. In the first tiny fraction of a second, it may have undergone a period called cosmic inflation, during which space expanded exponentially faster than light. This inflationary epoch, proposed by physicist Alan Guth in 1980, would have stretched quantum fluctuations in the infant universe to cosmic scales, seeding the structures that would eventually become galaxies and galaxy clusters. The evidence for inflation comes from several sources, including the remarkable uniformity of the universe on large scales and the specific patterns observed in ancient light from the cosmic microwave background. The mechanism of inflation remains uncertain. Most models propose a scalar field called the inflaton that dominated the universe's energy density during this epoch. The inflaton field had unusual properties. Its energy density remained nearly constant even as space expanded, creating a kind of cosmic anti-gravity that drove exponential expansion. When the inflaton field finally decayed, it released its energy as a flood of particles, reheating the universe and ending the inflationary epoch. This reheating may have produced all the matter and radiation that eventually formed galaxies and stars. Inflation solves several puzzles that the basic Big Bang theory cannot explain. First, there is the horizon problem. The cosmic microwave background has nearly the same temperature in every direction, even from regions of the sky so far apart that light has not had time to travel between them since the Big Bang. How did these regions come to the same temperature if they could never have been in contact? Inflation answers this by proposing that all these regions were once much closer together, close enough to reach thermal equilibrium before inflation stretched them apart. Second, there is the flatness problem. The geometry of the universe is very nearly flat, meaning the angles of a cosmic triangle sum to almost exactly 180 degrees. But if the universe started with even a tiny deviation from flatness, that deviation would have grown over time. For the universe to be as flat as we observe today, its initial geometry would have had to be fine-tuned to extraordinary precision. Inflation explains this by stretching space so dramatically that any initial curvature was smoothed away, like the surface of a balloon becoming flatter and flatter as it expands. Third, inflation explains why we do not see magnetic monopoles, hypothetical particles that many grand unified theories predict should have been produced in the early universe. If monopoles formed before inflation, they would have been diluted to undetectable densities as space expanded exponentially. This absence of monopoles, which should be detectable if they existed in significant numbers, is consistent with the inflationary picture. After inflation ended, the universe continued expanding but at a much slower rate. It was still extraordinarily hot, a plasma of quarks, electrons, photons, and other particles all interacting violently. The temperature was so high that atoms could not form. Any time a proton captured an electron, another photon would instantly blast them apart. The universe was opaque, filled with light that could travel no distance at all before being scattered. In this early plasma, matter and antimatter existed in nearly equal amounts. Quarks and antiquarks, electrons and positrons constantly appeared and annihilated in a seething quantum foam. But a tiny asymmetry, about 1 part in a billion, favoured matter over antimatter. For every billion antimatter particles that formed and annihilated, 1,000,000,001 matter particles formed. After all the annihilation was complete, that tiny surplus of matter remained. It would eventually become every star, planet, and living thing in the universe. The origin of this matter-antimatter asymmetry is one of the great unsolved problems in physics. As the universe expanded, it cooled. Around 3 minutes after the Big Bang, the temperature had dropped enough for protons and neutrons to fuse into the nuclei of light elements, primarily hydrogen and helium, with trace amounts of lithium. This process, called Big Bang nucleosynthesis, produced the abundances of light elements we observe today, roughly 75% hydrogen and 25% helium by mass. The agreement between predicted and observed abundances is one of the strongest confirmations of the Big Bang model. The precision of this prediction deserves emphasis. The equations governing nuclear reactions in the early universe are well understood. Physicists can calculate exactly how much helium, deuterium, lithium, and other light nuclei should have been produced during the first few minutes, given the temperature, density, and expansion rate. These calculations yield specific numbers that can be compared directly to observations. When astronomers measure the composition of the oldest stars and the most pristine intergalactic gas clouds, they find abundances that match the predictions with impressive accuracy. The deuterium abundance is particularly significant. Deuterium, or heavy hydrogen, consists of one proton and one neutron bound together. It is fragile, easily destroyed in stellar nuclear reactions. Deuterium observed in the universe today must therefore be primordial, surviving untouched since the Big Bang. Its measured abundance matches theoretical predictions within observational uncertainties. This is strong evidence that our understanding of the early universe is essentially correct. The nuclear reactions during this epoch determined the chemical starting point for the entire universe. All the hydrogen that exists today was created during these first few minutes. All the helium likewise. Later, in the cores of stars, these light elements would fuse into heavier ones: carbon, oxygen, iron, gold. Every atom in your body heavier than hydrogen traces back to a star that lived and died before our solar system formed. You are literally made of stardust, and that stardust was assembled from the primordial hydrogen and helium forged in the first minutes of cosmic history, but the universe remained a plasma for another 380,000 years. Only then did expansion cool it to about 3,000 degrees Celsius, a temperature at which electrons could finally combine with nuclei to form neutral atoms. This event, called recombination, had a dramatic consequence. Neutral atoms do not scatter light the way free electrons do. For the first time, photons could travel freely through space. The universe became transparent. This transition happened relatively quickly on cosmic timescales, over a period of perhaps 100,000 years. Before recombination, the universe was opaque, filled with light that could travel no distance at all before being scattered by free electrons. After recombination, it became the dark void of space we know today, transparent to light across vast distances. The photons released at recombination have been travelling through space ever since, preserving information about the universe at that primordial moment. The light released at that moment has been travelling through space ever since, stretched to longer and longer wavelengths as the universe expanded. Today, that ancient light has been stretched into the microwave region of the electromagnetic spectrum. Its temperature has cooled to just 2.7 degrees above absolute zero. We call it the cosmic microwave background, and it is one of the most important pieces of evidence we have for the Big Bang model. In 1964, two radio astronomers at Bell Telephone Laboratories in New Jersey were struggling with an annoying problem. Arno Penzias and Robert Wilson were trying to calibrate a large horn-shaped antenna for satellite communication experiments, but no matter what they did, they could not eliminate a persistent background hiss in their data. They cleaned pigeon droppings from the antenna. They checked for interference from nearby cities. They accounted for radio noise from our galaxy. Nothing worked. The hiss came from every direction equally, day and night, summer and winter. It was as if the entire sky were glowing faintly at microwave wavelengths. The antenna Penzias and Wilson were using had originally been built for a different purpose. It was part of a program to communicate with early communications satellites, designed to be extremely sensitive to faint signals. That sensitivity made it perfect for detecting something unexpected. The mysterious noise corresponded to a temperature of about 3.5 Kelvin, just a few degrees above absolute zero. It seemed to be coming from everywhere at once, with no identifiable source. What Penzias and Wilson had accidentally discovered was the cosmic microwave background radiation. They did not immediately recognize its significance, but physicists at nearby Princeton University did. Robert Dicke and his colleagues, including P.J.E. Peebles, David Wilkinson and Peter Roll, had been preparing to search for exactly this radiation. They had predicted that if the Big Bang theory was correct, the universe should be filled with remnant heat from its fiery beginning. Dickey's team was actually building their own detector to look for the CMB when they learned about the strange noise Penzias and Wilson had found. The serendipitous discovery by Penzias and Wilson confirmed this prediction spectacularly. They would share the 1978 Nobel Prize in Physics for their work. The Princeton theorists who had predicted the CMB did not receive the prize, though their contributions were crucial to understanding what had been found. The story of the cosmic microwave background prediction goes back even further. In the 1940s, physicist George Gamow and his colleagues Ralph Alpher and Robert Herman had worked out the basic physics of the early universe. They calculated how light elements would have formed in the first minutes after the Big Bang. As part of this work, they realized that the early universe must have been extremely hot, and that the leftover radiation from that hot beginning should still permeate space today. They even estimated its current temperature at about 5 Kelvin, remarkably close to the actual value. But their prediction was largely forgotten, and when Penzias and Wilson made their discovery, neither they nor most other astronomers knew about this earlier theoretical work. The forgetting of Gamow's prediction is itself a lesson in how science works. Good ideas can be ahead of their time, published in journals that the right people do not read, or simply overshadowed by other developments. When the CMB was discovered, physicists had to rediscover the theoretical framework that Gamow had developed 20 years earlier. Science does not always progress in straight lines. The cosmic microwave background is remarkable for several reasons. First, it is extraordinarily uniform. The temperature varies by only about 1 part in 100,000 across the entire sky. This uniformity tells us that the early universe was incredibly smooth, with matter and energy distributed almost perfectly evenly in every direction. Second, the spectrum of the radiation matches precisely what physicists call a black body, the kind of radiation emitted by an object in thermal equilibrium. This perfect blackbody spectrum, confirmed by NASA's Cosmic Background Explorer satellite in the early 90s, tells us that the early universe was indeed in thermal equilibrium, exactly as the Big Bang model predicts. A blackbody spectrum has a very specific shape determined by temperature alone. Any object in thermal equilibrium emits radiation with this characteristic distribution of wavelengths. The peak of the spectrum shifts to shorter wavelengths as temperature increases, and to longer wavelengths as temperature decreases. By measuring the CMB spectrum and identifying its peak, scientists determined that the radiation has a temperature of exactly 2.725 Kelvin, just a few degrees above absolute zero. This is what you get when you redshift radiation that was once at 3000 Kelvin, stretching it by a factor of roughly 1 to 100 as the universe expanded. When COBE measured the CMB spectrum, the data fit the theoretical blackbody curve so perfectly that scientists could hardly believe it. The match was better than any blackbody spectrum ever measured in a laboratory. The universe had been in thermal equilibrium to an astonishing degree. This confirmed that the CMB really was the remnant glow of the hot early cosmos, not some local source of radiation masquerading as a cosmic signal. COBE also made another crucial discovery. Using extremely sensitive instruments, it detected tiny variations in the CMB temperature across the sky. These fluctuations, measuring only about 100 millionths of a degree, were the seeds from which all cosmic structure grew. Slightly denser regions in the early universe had slightly higher temperatures. Over billions of years, these density variations would amplify through gravity to become the galaxies and galaxy clusters we observe today. The COBE team, led by John Mather and George Smoot, received the 2006 Nobel Prize for these discoveries. The detection of these fluctuations was a triumph of precision measurement. The temperature variations are so tiny that detecting them required cooling the instruments to temperatures near absolute zero and accounting for every possible source of contamination. The Milky Way itself emits microwaves that had to be carefully subtracted from the data. So does the solar system's dust. So do individual galaxies along the line of sight. Only after all these foreground sources were removed did the primordial fluctuations emerge, faint whispers from the dawn of time. But it is the tiny non-uniformities in the cosmic microwave background that are perhaps most important. Those variations of 1 part in 100,000 represent slight differences in density in the early universe. Regions that were slightly denser than average had slightly stronger gravity. Over hundreds of millions of years, that extra gravity attracted more matter, making those regions denser still. Eventually, these overdense regions collapsed to form the first stars and galaxies. The pattern of fluctuations in the cosmic microwave background is essentially a map of where all the structures in the universe came from. Satellites including NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck mission have mapped these fluctuations in exquisite detail. The WMAP satellite, launched in 2001, operated for 9 years and produced a full-sky map of the CMB with unprecedented precision. It orbited a point in space called L2, about 1.5 million kilometers from Earth in the direction opposite the Sun, where it could observe the sky without interference from Earth or the Moon. The WMAP data allowed cosmologists to determine the age and composition of the universe with remarkable accuracy. The Planck satellite, launched in 2009, did even better, mapping the CMB at multiple frequencies and with sharper angular resolution. Planck carried instruments sensitive to 9 different frequency bands, allowing it to separate the primordial CMB signal from various foreground emissions. Its detectors were cooled to just 1/10 of a degree above absolute zero, making them extraordinarily sensitive to the faint temperature variations across the sky. The resulting maps show the CMB in stunning detail, revealing features as small as a fraction of a degree across. These observations revealed the detailed pattern of hot and cold spots across the sky, a pattern that encodes information about the earliest moments of cosmic history. The spots are not random. They have characteristic sizes determined by the physics of sound waves in the early universe. Before recombination, the plasma of photons and matter supported acoustic oscillations, pressure waves bouncing back and forth like sound in a room. These waves had specific wavelengths determined by how far sound could travel in the age of the universe at that time. By analysing the sizes and distributions of hot and cold spots in the cosmic microwave background, cosmologists can extract fundamental information about the universe. The physics is subtle but powerful. Sound waves rippled through the early universe when it was still a plasma, creating a characteristic pattern of density variations at particular scales. These Brion acoustic oscillations, as they are called, left their imprint on the CMB and on the distribution of galaxies today. They serve as a standard ruler that cosmologists can use to measure how the universe has expanded over time. The acoustic peaks in the CMB power spectrum are like a cosmic fingerprint. The first peak corresponds to regions that had just completed one compression at the moment of recombination. The second peak corresponds to regions that had completed one compression and one rarefaction. Higher peaks correspond to more oscillations. The heights and positions of these peaks depend sensitively on the properties of the universe, including its geometry, its expansion rate, and its composition of ordinary matter, dark matter, and dark energy. By fitting theoretical models to the observed peaks, cosmologists can determine these properties with remarkable precision. From CMB observations, scientists can determine the universe's age, its geometry, its composition, and the rate at which it's expanding. They can distinguish between different models of inflation and test predictions of the standard cosmological model. The CMB is not just a historical artifact, it is an ongoing laboratory for fundamental physics. The CMB also provides evidence for inflation. The fluctuations have a particular statistical pattern, slightly more power at large scales than at small scales, exactly as inflation predicts. They are also Gaussian, meaning they follow a normal distribution with no preferred direction or asymmetry. This is what you would expect if the fluctuations originated from quantum processes during inflation. Any exotic physics that might have operated in the early universe would likely leave non-Gaussian signatures that we do not observe. According to Planck satellite data released in 2015, the universe is 13.799 billion years old, with an uncertainty of about 38 million years, a precision that would have seemed impossible just decades earlier. The geometry of space is flat, meaning the angles of a cosmic triangle add up to exactly 80 degrees, just as they do in the geometry you learned in school. And the Hubble constant calculated from cosmic microwave background measurements using the standard cosmological model is approximately 7.4 km per second per megaparsec. This last number would become extraordinarily controversial. Before we confront the crisis that number has created in modern cosmology, we need to understand the large-scale structure of the universe that expansion has produced. The universe is not a uniform sea of galaxies scattered randomly through space. Instead, it is organized into a vast cosmic web of filaments, walls, and voids that spans billions of light years. Imagine a soap bubble bath where bubbles of various sizes cling together. The surfaces where bubbles meet form sheets and edges. Where several bubbles come together, their meeting points create vertices. The universe has a similar structure, but on scales almost impossible to comprehend. Galaxies are not distributed uniformly through space. They cluster along filaments, enormous threads of matter stretching hundreds of millions of light years. Where multiple filaments intersect, galaxies pile up into dense clusters containing thousands of members. Between the filaments lie cosmic voids, immense regions where galaxies are sparse or absent altogether. The largest known filamentary structures span mind-boggling distances. The Sloan Great Wall, discovered in 2003, stretches approximately 1.4 billion light-years across the sky. even larger structures may exist. Some astronomers have reported detecting features spanning several billion light-years, though the reality of these structures remains debate. What is certain is that the universe has organization at scales far beyond individual galaxies. Galaxy clusters represent the densest nodes of the cosmic web. The Virgo cluster, our nearest major cluster neighbour at about 54 million light-years away, contains over 1/300 known galaxies. The Coma cluster, significantly farther at about 320 million light-years, holds thousands of galaxies bound together by their mutual gravity. These clusters are not isolated. They are connected by filaments of matter, highways of galaxies linking one concentration to the next. This foam-like architecture was not immediately obvious to astronomers. For most of the 20th century, technology limited observations to relatively nearby galaxies. The three-dimensional structure of the universe remained hidden because distances to individual galaxies were difficult to measure. But beginning in the 1970s and accelerating in subsequent decades, redshift surveys changed everything. By measuring the redshifts of thousands and eventually millions of galaxies, astronomers could determine not just their positions on the sky, but their distances from Earth. Three-dimensional maps of the universe became possible. The first major discovery from these surveys was the existence of the cosmic voids themselves. In 1978, separate teams identified large regions with far fewer galaxies than expected. These were not small gaps, they were bubbles of relative emptiness spanning tens to hundreds of millions of light-years. The Boots Void, discovered in 1981, stretches nearly 30 million light-years across and contains only a handful of galaxies where thousands might be expected. Within its vast emptiness, you could travel for more than 100 million light-years without encountering a single galaxy. As surveys grew larger, the interconnected web structure emerged. The Center for Astrophysics Redshift Survey in the 1980s revealed striking features, including the Great Wall, a sheet of galaxies extending over 500 million light-years. The 2-degree field galaxy redshift survey mapped the positions of more than 200,000 galaxies. The Sloan Digital Sky Survey, which began observations in 2000, has mapped the positions of more than 1 million galaxies. The resulting three-dimensional maps reveal cosmic filaments stretching like highways through the universe. Galaxy clusters glowing at their intersections and vast dark voids occupying the spaces between. These structures represent the universe's most prominent features. The cosmic web contains most of the matter in the universe, with roughly half of all galaxies residing within filaments. The voids, while dominating the volume of space, contain far less mass. They are true cosmic deserts, regions where the density of matter falls to 15 or 20% of the cosmic average. This structure did not emerge by accident. It grew from those tiny density fluctuations imprinted in the cosmic microwave background. Regions that started slightly over-dense attracted more matter through gravity. Regions that started slightly under-dense lost matter to their denser neighbours. Over billions of years, this process amplified the initial variations into the dramatic structure we observe today. Dense regions collapsed into galaxies and clusters. Underdense regions expanded into voids. Computer simulations can reproduce this process with remarkable fidelity. Starting from initial conditions matching the fluctuations observed in the CMB, simulations evolve the universe forward using the laws of gravity and fluid dynamics. The results look strikingly similar to observed galaxy surveys. Filaments form, clusters develop at their intersections, voids expand between them. The match between simulation and observation provides powerful confirmation that we understand the basic physics of cosmic structure formation. What makes cosmic voids particularly interesting for understanding expansion is what happens inside them. In the dense filaments and clusters, gravity is strong. Matter attracts matter, structures hold together, and the expansion of the universe is locally resisted. But in voids, gravity is weak. There is not enough mass to slow the expansion significantly. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward. The dominant force inside cosmic voids is not gravity, it is something else entirely. In 1998, 2 independent teams of astronomers set out to measure how quickly the expansion of the universe was slowing down. They were using type supernovae, a particular kind of stellar explosion that occurs when a white dwarf star accumulates material from a companion until it crosses a critical mass threshold and detonates. These explosions have a consistent intrinsic brightness, meaning astronomers can determine how far away they are by measuring how dim they appear. Type Ia supernovae are extraordinarily useful for cosmology precisely because of this consistency. When a white dwarf crosses the Chandrasekhar limit of about 1.4 solar masses, the result is always the same, a thermonuclear runaway that completely destroys the star. The explosion releases a characteristic amount of energy, producing a brief flash of light visible across billions of light years. By comparing how bright a Type Ia supernova appears to how bright we know it actually is, we can calculate how far away it must be. Both teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, expected to find that distant supernovae were brighter than their redshifts predicted. This would mean those supernovae were closer than expected, which would mean the expansion of the universe had slowed since their light was emitted billions of years ago. Gravity, everyone assumed, had been acting as a brake on cosmic expansion since the Big Bang. The reasoning seemed sound. The universe is filled with matter, and matter attracts other matter through gravity. As galaxies rush apart, gravity pulls on them, slowing their recession. The expansion should be decelerating. By measuring how much deceleration had occurred, cosmologists hoped to determine the average density of matter in the universe and thereby predict its ultimate fate. If the density exceeded a critical value, gravity would eventually halt the expansion and reverse it, leading to a big crunch. If the density fell below the critical value, expansion would continue forever, with the universe gradually becoming emptier and colder. What both teams discovered was the opposite. The distant supernovae were dimmer than expected. They were farther away than their redshifts predicted. The expansion of the universe had not been slowing down, it had been speeding up. This result was so unexpected that both teams spent months checking their data, looking for errors, considering alternative explanations. Could dust between us and the supernovae be making them appear dimmer? The teams carefully selected supernovae based on their colours to minimise dust effects. Could there be something unusual about ancient supernovae that made them intrinsically fainter? No physical mechanism could explain why supernovae billions of years ago would be systematically different from the nearby ones. Could there be a systematic error in the analysis? Every possibility was examined. The conclusion held: the universe's expansion is accelerating. The announcement came in 2 papers published in 1998, one from each team. The results were met with astonishment and initially skepticism. The idea that the expansion was speeding up contradicted decades of cosmological thinking. But as more data accumulated, as independent lines of evidence converged, the result became inescapable. The supernova observations were confirmed by measurements of the cosmic microwave background and by studies of how galaxies cluster. Everything pointed in the same direction. The expansion of the universe is accelerating. The confirmation came from multiple independent sources. The cosmic microwave background measurements from WMAP and later Planck required a universe dominated by some form of energy with negative pressure, exactly what the supernova teams had found. Studies of how galaxies cluster at different epochs in cosmic history showed that the clustering pattern evolved in a way consistent with accelerating expansion. Measurements of the integrated Sachs-Wolf effect, a subtle imprint that large-scale structures leave on the CMB, also supported the existence of dark energy. No single observation would have been convincing alone. Together they formed an overwhelming case. This discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. It also presented physics with one of its deepest mysteries. For the expansion to be accelerating, something must be providing a repulsive force that opposes gravity. This something must be spread throughout the universe, present in every region of space. It must have negative pressure, a property that in the context of general relativity causes space itself to push outward. And it must make up the majority of the energy content of the cosmos. The concept of negative pressure deserves explanation because it sounds paradoxical. In everyday life, pressure is always positive. Air pressure pushes outward against the walls of a balloon. Water pressure pushes outward in all directions. But in general relativity, both energy density and pressure contribute to gravity. Positive energy density causes gravitational attraction. Positive pressure also causes gravitational attraction, but negative pressure causes gravitational repulsion. If a substance has negative pressure, it pushes space apart rather than pulling it together. Dark energy has exactly this property. Its energy density is positive, but its pressure is negative, and the negative pressure dominates. The result is a net repulsive effect that accelerates cosmic expansion. The more space there is, the more dark energy there is, and the faster the expansion accelerates. This is a runaway process that will dominate the future of the cosmos. Scientists named this mysterious component dark energy. They called it dark because we cannot see it directly. We detect it only through its gravitational effects on the largest scales. And despite more than 2 decades of research since its discovery, we still have almost no idea what it actually is. The term dark energy is somewhat misleading. It is not energy in the conventional sense that you might store in a battery or release by burning fuel. It is more like a property of space itself, a tendency for the fabric of the cosmos to push outward. But even this description is inadequate. We do not really understand what dark energy is. We can only describe what it does. The simplest explanation for dark energy is that it is a cosmological constant, an intrinsic energy density of empty space itself. Remember Einstein's greatest blunder? His cosmological constant was introduced for the wrong reason, to create a static universe that does not exist. But mathematically, it is a valid term in the equations of general relativity. If empty space has a constant energy density everywhere, that energy would cause exactly the kind of accelerating expansion we observe. The idea that empty space could have energy seems paradoxical. How can nothing contain something? But quantum mechanics tells us that space is never truly empty. Even in a perfect vacuum, devoid of all matter and radiation, quantum fluctuations cause virtual particles to pop in and out of existence constantly. These fluctuations contribute energy to the vacuum. In principle, this vacuum energy could act as a cosmological constant driving cosmic acceleration. The quantum vacuum is a strange place. According to the Heisenberg uncertainty principle, energy can be borrowed from the vacuum for brief periods, allowing particle-antiparticle pairs to pop into existence before annihilating each other. These virtual particles exist for timescales so short that they cannot be directly detected, but their effects are measurable. The Casimir effect, for example, arises from the difference in vacuum fluctuations between 2 closely spaced metal plates. The effect has been measured in laboratories and matches quantum mechanical predictions precisely. The problem is that when physicists try to calculate what this vacuum energy should be, from first principles using quantum mechanics, they get a number that is catastrophically wrong. The predicted value exceeds the observed value by a factor of roughly 10 to the 120th power. This is widely considered the worst prediction in the history of physics. Either our understanding of quantum mechanics is deeply flawed, or our understanding of gravity at cosmological scales is incomplete, or both. This discrepancy is known as the cosmological constant problem, and it has resisted the solution for decades. To appreciate how bad this prediction is, consider that 10 to the 120th power is larger than the number of atoms in the observable universe multiplied by itself roughly 10 times. The quantum prediction for vacuum energy is not just a little off. It is off by more than any other prediction in the history of science. If the vacuum energy really were that large, the universe would have expanded so rapidly that atoms could never have formed. The fact that we exist at all means the actual cosmological constant must be many, many orders of magnitude smaller than the quantum calculation predicts. The vast mismatch between theoretical prediction and observation suggests that something fundamental is missing from our understanding. Perhaps some unknown mechanism cancels most of the vacuum energy, leaving only the tiny residual we observe. Perhaps the calculation itself is flawed in ways we do not understand. Perhaps dark energy is not vacuum energy at all, but something else entirely. Several theoretical approaches have attempted to explain why the cosmological constant might be so small. Supersymmetry, a proposed extension of particle physics, would predict that every known particle has a partner particle with different spin. The vacuum fluctuations from these partner particles would have opposite sign to the known particles, potentially cancelling their contributions to vacuum energy. But no supersymmetric particles have been found despite extensive searches at particle accelerators, and even with supersymmetry, the cancellation would need to be extraordinarily precise to produce the tiny residual we observe. String theory, another theoretical framework, suggests that what we perceive as particles are actually tiny vibrating strings. In some versions of string theory, the cosmological constant can take many different values in different regions of space-time, and we happen to live in a region where it is small enough to allow galaxies and stars and life to form. This anthropic argument is philosophically controversial. It explains why we observe a small cosmological constant by noting that we could not exist to observe a large one, but it does not explain why the constant has the specific value it does. Alternative explanations for dark energy abound. Perhaps it is not constant, but rather a dynamic field that evolves over time, a concept physicists call quintessence. In quintessence models, dark energy can vary in strength across cosmic history. It might have been different in the past and could be different in the future. Perhaps the acceleration is not caused by a new form of energy at all, but by a modification to general relativity on cosmic scales. Perhaps gravity itself works differently at cosmological distances than it does locally. Perhaps our interpretation of the supernova data is wrong in some subtle way we have not identified. Quintessence models are named after the ancient Greek concept of a fifth element, the quintessence that was thought to compose the heavens. In these models, dark energy arises from a scalar field that pervades space, similar to the Higgs field discovered at the Large Hadron Collider. The field has potential energy that drives cosmic acceleration, but unlike a cosmological constant, the field can evolve as the universe expands. Different quintessence models predict different evolution histories, which could potentially be tested by measuring how the expansion rate has changed over cosmic time. What we know for certain is that dark energy dominates the universe. According to observations from the Planck satellite and other sources, dark energy makes up approximately 68% of the total energy content of the cosmos. Dark matter, another mysterious component that we detect through its gravitational influence on galaxies and galaxy clusters, makes up about 27%. Ordinary matter, the atoms that make up stars and planets and people, comprises a mere 5%. We understand that 5% reasonably well. We have decent models for the 27%, though we do not know what dark matter particles actually are. But the 68%, the majority of everything that exists, we have almost no understanding of its fundamental nature. This situation represents one of the most humbling realizations in the history of science. After centuries of progress, after developing quantum mechanics and general relativity and the standard model of particle physics, we find ourselves unable to explain what most of the universe is made of. As if dark energy were not mystery enough, cosmology now faces a crisis that threatens to upend our standard model of how the universe works. The crisis goes by the name the Hubble tension, and it has been growing more severe with every passing year. Recall that the Hubble constant describes how fast the universe is expanding. If you measure the velocity at which distant galaxies are receding and the distances to those galaxies, you can calculate the expansion rate. This is the local or late universe measurement, because you are observing objects in the nearby universe as it exists today. The method involves building what astronomers call a cosmic distance ladder. You start with distances you can measure directly, like the distances to nearby stars using parallax, the tiny shift in a star's apparent position as Earth orbits the Sun. From there, you identify standard candles, objects with known intrinsic brightness, and use them to reach farther out. Cepheid variable stars serve this purpose for distances up to about 100 million light-years. Type Ia supernovae extend the reach to billions of light-years. By calibrating each rung of the ladder against the previous one, astronomers can measure distances across cosmic scales. Combining these distances with redshift measurements gives the expansion rate directly. The recession velocity of a galaxy is proportional to the stretching of its light, which we can measure precisely. Dividing velocity by distance gives the Hubble constant. This approach, refined over decades and now employing some of the most sophisticated astronomical instruments ever built, consistently yields values around 73 to 74 kilometers per second per megaparsec. There is another way to determine the Hubble constant. The cosmic microwave background contains information about the early universe, including its density, composition, and expansion rate at the time the CMB was released. Using the standard cosmological model called lambda CDM, where lambda represents the cosmological constant and CDM stands for cold dark matter, you can calculate what the expansion rate should be today, given the conditions 380,000 years after the Big Bang. This is the early universe measurement. The physics underlying this calculation is well understood. The fluctuations in the CMB have characteristic sizes set by the sound horizon, the distance sound waves could travel in the early universe before recombination. This serves as a standard ruler imprinted on the CMB. By measuring the angular size of these fluctuations and knowing the physics of how the universe expanded since then, cosmologists can work out the current expansion rate. The Planck satellite measured these fluctuations with exquisite precision, and the resulting Hubble constant comes out to about 7.4 kilometers per second per megaparsec. These two methods should give the same answer. They do not. The difference is about 8 to 9%. This might not sound like much, but both measurements have become extraordinarily precise. The statistical uncertainty in each is only 1 to 2%. For the measurements to agree, one or both would have to be wrong by multiple times their quoted errors. The probability of this happening by chance is extremely small. The tension has reached what physicists call 5 sigma significance. In particle physics, 5 sigma is the threshold for claiming a discovery. There is less than a 1 in a million chance that the discrepancy is random fluctuation. Something real is going on here. The implications are profound. If both measurements are correct, the universe is expanding faster locally than our models predict it should be based on its early conditions. Either our understanding of the early universe is incomplete, or our measurements of the local universe contain systematic errors we have not identified, or there is some new physics that modifies how the universe evolves between the CMB era and today. At first, researchers suspected measurement errors. Perhaps the distance ladder used for local measurements had systematic biases. Perhaps some step in the calibration chain was flawed. Enormous effort has gone into checking every rung of the ladder. The James Webb Space Telescope has now confirmed the Hubble measurement using the same types of stars Hubble used, but with far superior resolution. The results match. The Webb data rules out the possibility that the local measurements are significantly biased by errors in how we measure stellar distances. Different methods for measuring distances have converged on similar values. The tip of the red giant branch method, which uses a different type of star as a standard candle, gives values consistent with the Cepheid-based measurements. Gravitational lensing of distant quasars provides another independent check. Even gravitational waves from merging neutron stars, which can serve as standard sirens with distances independent of the traditional cosmic distance ladder, yield values in the high range. On the early universe side, multiple experiments have confirmed the Planck results. The Atacama Cosmology Telescope and the South Pole Telescope, ground-based instruments studying the CMB at high resolution, find values consistent with Planck. The agreement among early universe measurements is remarkable. In January 2025, a new measurement using supernovae in the Coma cluster added further confirmation. The Hubble constant came out to 76.5 km per second per megaparsec, even higher than previous local values. The discrepancy is not shrinking. It appears to be robust. If the measurements are correct, then the standard cosmological model is incomplete. Something about the lambda CDM model does not accurately describe how the universe has evolved from the early plasma we see in the CMB to the expanding cosmos we observe today. Many solutions have been proposed. Perhaps there was an additional form of energy in the early universe, now called early dark energy, that gave the cosmos an extra kick after the Big Bang and then faded away. This additional energy would have sped up the early expansion, causing the CMB to give a different prediction for the current rate. Perhaps dark energy is not constant but has varied over time. If dark energy was weaker in the past, the universe would have expanded more slowly early on and would need to be expanding faster now to produce the CMB features we observe. Perhaps our understanding of gravity needs modification on cosmological scales. Perhaps there is some unknown systematic effect linking the early and late measurements that we have not identified. Recent data from the Dark Energy Spectroscopic Instrument has added an intriguing twist. Analysis of how galaxies cluster at different epochs in cosmic history suggests that dark energy may not be constant after all. The data hint that dark energy was stronger in the past and has been weakening over time. If confirmed, this would require replacing the cosmological constant with something more dynamic and would fundamentally alter our understanding of cosmic evolution. DESI operates differently from supernova surveys. Instead of measuring individual exploding stars, it maps the three-dimensional distribution of millions of galaxies across vast volumes of space. The clustering pattern of these galaxies preserves an imprint of sound waves that propagated through the early universe, the baryon-acoustic oscillations. These oscillations create a characteristic scale, preferred distance between galaxies, that serves as a standard ruler for measuring cosmic expansion. By measuring this ruler at different distances, which corresponds to different cosmic epochs, DESI can trace how the expansion rate has changed over billions of years. The results, released in 2004 and updated in 2025, hint at something unexpected. Dark energy appears to have been behaving differently than the cosmological constant predicts. Its effects seem to have weakened over time, with the universe expanding less aggressively in recent epochs than a constant dark energy would produce. If dark energy truly evolves, the implications are profound. The cosmological constant represents the simplest possible form of dark energy, a fixed energy density that never changes, an intrinsic property of space itself. Evolving dark energy requires something more complex, perhaps a dynamic field that fills space and changes as the universe ages. Theorists have proposed such fields under names like quintessence, but none has been definitively detected. The DESI results have not yet reached the statistical threshold required for a definitive discovery. More data and analysis are needed, but the hint of evolving dark energy, combined with the persistent Hubble tension, suggests that our standard cosmological model may be due for revision. No solution has emerged as clearly correct. The tension remains unresolved. Cosmology is genuinely in crisis, facing a disagreement between observation and theory that strikes at the heart of our standard model. One proposed explanation for the Hubble tension brings us back to cosmic voids and what happens inside them. Some researchers suggest that Earth might be located inside an unusually large underdense region of the universe, a cosmic void that distorts our local measurements. The idea is conceptually simple but has profound implications. Cosmic voids are not static regions of empty space. They are dynamic environments where the balance of forces differs from the cosmic average. In dense regions like galaxy clusters, gravity pulls matter together, resisting the expansion of space. But in voids, there is not enough matter for gravity to dominate. Dark energy, the mysterious force accelerating cosmic expansion, becomes the ruling power. Voids expand faster than the universe as a whole. If we live inside a void, the matter surrounding us is denser than the matter nearby. That surrounding matter exerts a gravitational pull outward, adding extra velocity to nearby galaxies beyond what cosmic expansion alone would produce. Galaxies near the void's edge are being pulled toward the denser surrounding regions. This creates an outflow, a systematic motion of galaxies away from the void center in addition to the general cosmic expansion. When we measure those galaxy velocities and use them to calculate the expansion rate, we get a value that is higher than the true cosmic average. We are not measuring the universe incorrectly. We are measuring it from inside a hole that makes our local expansion appear faster than it really is. Evidence for such a local void exists. Galaxy counts in our cosmic neighborhood show that we live in a region where matter density is roughly 15 to 20% lower than the cosmic average. This structure, sometimes called the KBC void after the researchers who characterized it in 2013, stretches approximately 2 billion light-years across. We do not sit at its exact center, but we are close enough that its effects could be significant. The void was identified by counting galaxies across the sky and comparing the observed distribution to what standard cosmology predicts. The researchers found a significant deficit of galaxies in our local region, extending in all directions for roughly 1 billion light-years. The deficit is not subtle. Where the cosmic average predicts a certain number of galaxies, we see 20% fewer. The void hypothesis elegantly explains why local measurements give higher expansion rates than cosmic microwave background measurements. The CMB tells us about the average expansion of the universe, unaffected by our local conditions. It samples the entire visible universe, averaging over voids and clusters alike. Local measurements are biased by the void we inhabit. They capture the sum of cosmic expansion plus the outflow velocity induced by the void's gravitational environment. The true Hubble constant might indeed be around 6, with our local value of 73 reflecting a peculiar velocity added by the void. Researchers have tested this idea by modelling what a void of the KBC's size and depth would do to our measurements. The results are promising. A void roughly a billion light-years in radius with a 20% density deficit can produce an apparent boost to the Hubble constant of the right magnitude. The observed bulk flows of galaxies in our region, their coherent motion beyond simple cosmic expansion, match what the void model predicts. However, this explanation has challenges. A void large enough and deep enough to account for the full Hubble tension would be extraordinarily rare according to standard cosmology. Computer simulations of how the universe evolved from the Big Bang rarely produce voids this extreme. The initial density fluctuations that grew into cosmic structure through gravity simply do not create many voids this large and this empty. Finding ourselves inside one would violate the cosmological principle, the assumption that no location in the universe is special. We would be living in a statistically improbable place. This is philosophically troubling. The cosmological principle has been a guiding assumption of modern cosmology for decades. It states that on large enough scales, the universe looks the same from every location. No place is privileged. This assumption simplifies the mathematics enormously and seems to be confirmed by the remarkable uniformity of the cosmic microwave background. If we actually occupy an unusual location, many of our conclusions about the universe might need revision. Some scientists embrace this possibility. They argue that rare events happen somewhere, and we might simply be the observers who happen to live in a rare void. The universe is large enough that improbable configurations must exist somewhere. We cannot rule out that we are that somewhere. Others find it troubling and seek alternative explanations. They prefer solutions that preserve the cosmological principle, attributing the Hubble tension to new physics rather than unusual geography. If dark energy evolves over time, for instance, the tension could be resolved without invoking special locations. The debate continues, and the resolution will require even more precise measurements of our cosmic surroundings and the expansion history of the universe. New surveys mapping millions of galaxies across billions of light-years will reveal whether structures as extreme as the KBC void are common or are rare. If many such voids exist, our location becomes less special. If they are truly rare, the cosmological principle may need modification. What the void discussion illustrates is how intimately connected cosmic expansion is to the structures expansion creates. Voids are not just empty spaces, they are regions where dark energy dominates, where gravity's influence is minimal, where the fabric of space stretches fastest. Understanding how voids form, evolve, and affect our observations is crucial for understanding the expansion of the universe itself. Inside cosmic voids, we see dark energy in its purest form. Without dense matter to counteract its repulsive pressure, dark energy reigns supreme. Voids expand faster than the cosmic average. Their boundaries push outward against the surrounding filaments. The universe's accelerating expansion is most visible in these vast empty regions. Studying void properties offers a unique window into dark energy's nature. If dark energy is truly constant, voids should expand at a predictable rate that we can calculate. If dark energy varies in time or space, voids at different distances, and thus different cosmic epochs, should show different expansion rates. By measuring void shapes and sizes across cosmic history, researchers can test whether the cosmological constant model is correct. The shapes of voids also carry information. In a universe dominated by a true cosmological constant, voids should remain approximately spherical as they expand. If dark energy has spatial variations, or if there are unknown forces at play, voids might become distorted. Precision measurements of void shapes, now becoming possible with large galaxy surveys, can distinguish between dark energy models. Where does this expansion lead? If the universe continues accelerating, driven by dark energy that remains constant or even strengthens over time, the future of the cosmos is bleak beyond imagining. The first consequence of accelerating expansion is isolation. As space stretches faster and faster, distant objects recede beyond our ability to observe them. The cosmic horizon, the boundary beyond which light cannot reach us, exists because the universe has a finite age. Light has only had 13.8 billion years to travel. Objects whose light has not yet reached us are beyond this horizon. But in an accelerating universe, a second horizon becomes important, the event horizon. Beyond a certain distance, objects are receding so fast that light emitted now will never reach us no matter how long we wait. New space is being created between us faster than light can cross it. These objects are not just currently invisible, they are permanently beyond our reach. As acceleration continues, this event horizon shrinks. Galaxies that we can see today will eventually pass beyond it, their light redshifted to invisibility as they fall over the cosmic edge. The Andromeda Galaxy, currently approaching us due to our mutual gravitational attraction, will merge with the Milky Way in about 4.5 billion years. But galaxies beyond our local group are already receding. Within about 150 billion years, galaxies beyond our local supercluster will have passed beyond the event horizon, their light fading to undetectable levels as they disappear forever. The merger of the Milky Way and Andromeda deserves attention, because it illustrates how gravity can still triumph locally, even as cosmic expansion dominates globally. These two galaxies are massive enough and close enough that their mutual gravitational attraction overcomes the expansion of space between them. They are approaching each other at roughly 110 kilometers per second. For decades, astronomers believed a collision in about 4 to 5 billion years was essentially certain. However, more recent analysis incorporating data from the Gaia spacecraft has introduced some uncertainty into this timeline. The gravitational influences of other nearby galaxies, particularly the Large Magellanic Cloud and Triangulum Galaxy, may affect the collision trajectory. Current estimates suggest there remains a significant probability of eventual merger, though the exact timing and certainty are less definitive than previously thought. If the merger occurs as most models predict, their billions of stars will pass through each other like two swarms of bees, their gas clouds colliding and triggering bursts of new star formation. Over hundreds of millions of years, the merged system would settle into a new giant elliptical galaxy, sometimes called Milkdromda or Milkonda by astronomers with a sense of humour. This merged galaxy will become the dominant structure in our local universe. The other galaxies of the local group, about 80 smaller systems including the Magellanic Clouds, will gradually fall into this central mass over the following billions of years. The local group will become a single super-galaxy surrounded by expanding void. Meanwhile, everything else recedes. The Virgo cluster, the nearest large cluster of galaxies at about 54 million light-years, is currently receding from us at about 200 kilometers per second. It will pass beyond our event horizon in roughly 150 billion years. The Coma cluster, the great superclusters, the cosmic web itself, all will fade from view as expansion carries them away faster than light can travel. Civilizations arising in that distant future would look out at a nearly empty sky. They would see their own stars, the stars of their merged galaxy, and nothing else. No distant galaxies, no cosmic web, no hint of the vast universe that once surrounded them. They might conclude they live in a small, static cosmos. The evidence for the Big Bang, for cosmic expansion, for the existence of dark energy would have vanished beyond their horizon. The universe would be lying to them by hiding its own nature. This is not merely a philosophical point, it has practical implications for cosmology. Much of what we know about the universe comes from observing distant objects, the cosmic microwave background, high redshift galaxies, type Ia supernovae at cosmic distances. Future cosmologists will be denied these tools. They will live in an observationally impoverished universe where the fundamental discoveries we have made would be impossible to reproduce. Imagine intelligent beings evolving in that distant era. They would have no way of knowing the universe began in a hot Big Bang. The cosmic microwave background, our smoking gun evidence for that beginning, would have redshifted to undetectable wavelengths. Distant galaxies, which show us how the universe looked in the past, would have vanished beyond the horizon. These future beings might develop sophisticated physics and astronomy, but they would reach fundamentally wrong conclusions about their cosmos. They might believe the universe is small, static, and eternal. They would have no reason to suspect otherwise. This raises a disturbing question about our own cosmological conclusions. Are we also missing evidence because it has already disappeared beyond some horizon we do not recognize? Probably not on the same scale, but the question highlights how dependent our understanding is on our particular moment in cosmic history. We are cosmologically privileged to exist when we do, but this is only the beginning of the end. About 1 trillion years from now, star formation will cease. Stars form when clouds of hydrogen gas collapse under their own gravity. But the raw material for new stars is finite. Some gas gets locked up in stellar remnants, some gets ejected into intergalactic space by supernova explosions and stellar winds, some gets consumed in existing stars. Eventually the reservoir runs dry. The last generation of stars will ignite from the final available gas clouds, and after that no new stars will form. The timeline of stellar extinction follows a predictable sequence. The most massive stars, the brilliant blue giants that burn so brightly, will be the first to go. They exhaust their fuel in mere millions of years and have already died countless times since the universe began. Stars like our Sun, medium-sized yellow dwarfs, last about 10 billion years. Our Sun is roughly halfway through its main sequence lifetime and will swell into a red giant in about 5 billion years, eventually shedding its outer layers and leaving behind a white dwarf. The existing stars will continue to shine, of course. Red dwarfs, the smallest and most common stars, burn their fuel so slowly that they can shine for trillions of years. Our own Sun, a yellow dwarf, will exhaust its hydrogen fuel in about 5 billion years, swelling into a red giant and eventually shrinking to a white dwarf. But red dwarfs will persist far longer. A star with 1/10 the Sun's mass can burn for 10 trillion years or more. Red dwarfs are remarkable objects. They make up perhaps 3/4 of all stars in the Milky Way, though they are so dim that none are visible to the naked eye. The nearest star to our Sun, Proxima Centauri, is a red dwarf. These stars burn hydrogen so slowly because their cores are fully convective, meaning the entire star participates in nuclear fusion rather than just a central region. Fresh hydrogen fuel constantly cycles into the burning zone while processed helium moves outward. This efficient mixing allows red dwarfs to convert a much larger fraction of their mass into energy compared to larger stars. Some red dwarfs burning today will still be shining in 10 trillion years, long after every other type of star has died. But even they will eventually exhaust their fuel. The last red dwarfs will glow faintly in a universe otherwise dark final embers of the stellar era, and then they too will fade. After the last star burns out, the universe enters what physicists call the degenerate era. The only remaining structures will be stellar corpses, white dwarfs, neutron stars, and black holes. These remnants will persist for timescales that dwarf the current age of the universe, but they are not immortal. White dwarfs are the cause of dead stars like our Sun. They no longer generate energy through nuclear fusion, but instead glow from residual heat, gradually cooling over billions and trillions of years. A typical white dwarf begins with a surface temperature of perhaps 100,000 degrees and cools from there. After 1 billion years, it might be down to 10,000 degrees. After 10 billion years, perhaps 5,000 degrees. The cooling slows as the temperature drops, following a power law that extends the process over immense timescales. Eventually they will reach thermal equilibrium with the background temperature of the universe and become black dwarfs, invisible lumps of crystallized carbon and oxygen. No black dwarfs exist yet because the universe is not old enough for any white dwarf to have cooled completely, but they will eventually constitute a significant fraction of the remaining matter. White dwarfs have a maximum mass, the Chandrasekhar limit, of about 1.4 solar masses. Above this limit, electron degeneracy pressure cannot support the star against gravity, and it collapses further. Most white dwarfs are considerably below this limit, typically around 0.6 solar masses. They are Earth-sized objects with the mass of a star, incredibly dense but stable against further collapse. Neutron stars are the collapse cores of more massive stars, incredibly dense objects where matter has been compressed to nuclear densities. A teaspoon of neutron star material would weigh billions of tons. These objects will also persist for immense timescales, slowly cooling and potentially changing phase as their interiors settle into exotic states of matter. Neutron stars are even more extreme than white dwarfs. They typically have masses between 1.4 and 2 solar masses compressed into spheres only about 20 kilometers across. At these densities, protons and electrons have merged into neutrons, forming a degenerate neutron fluid that resists further compression. The surfaces of neutron stars can reach temperatures of millions of degrees immediately after formation, but they cool over time, eventually becoming cold dark remnants. Some neutron stars spin rapidly and emit beams of radiation, appearing to pulse as the beams sweep past Earth. These are pulsars, and they provide some of the most precise clocks in the universe. But even pulsars slow down over time as they radiate energy. Eventually, all neutron stars will stop spinning and become cold, dark masses invisible except through their gravitational effects. About 10 to the 37th years from now, the protons that make up ordinary matter may begin to decay. This process, predicted by some grand unified theories of particle physics but never observed, would gradually dissolve all remaining matter into radiation. White dwarfs and neutron stars would evaporate, leaving nothing but diffuse particles. Whether proton decay actually occurs remains an open question in physics. Many grand unified theories predict it should happen on these timescales, but the standard model of particle physics does not require it, and decades of searching have produced no confirmed detections. The search for proton decay has been ongoing for decades. Giant underground detectors filled with purified water watch for the telltale flash of light that would signal a proton falling apart. So far, none has been seen. The current experimental lower limit on the proton lifetime is about, say, 10 to the 34th years Putsu, which means protons are stable for at least that long. But grand unified theories, which attempt to merge the strong, weak, and electromagnetic forces into a single framework, typically predict proton decay at timescales of 10 to the 36th to 10 to the 38th years. If these theories are correct, protons are not truly stable, they just decay very slowly. If protons decay, the consequences for the far future are profound. All ordinary matter is made of protons and neutrons bound together in atomic nuclei, surrounded by electrons. If protons decay, atomic nuclei fall apart. If nuclei fall apart, atoms cannot exist. Over timescales of 10 to the 37th years, white dwarfs would gradually dissolve into radiation. Neutron stars, which contain neutrons that would also decay, would evaporate. Black dwarfs that had cooled to invisibility would slowly fade entirely from existence. The only matter remaining would be whatever decay products the protons left behind, likely positrons and pions that would themselves decay into lighter particles and radiation. Black holes would be the last substantial objects. They seem eternal, trapping everything that falls into them forever. But Stephen Hawking demonstrated in 1974 that black holes slowly radiate energy through a quantum process now called Hawking radiation. Near the event horizon, pairs of virtual particles constantly pop in and out of existence. Occasionally one particle falls into the black hole while the other escapes. The escaping particle carries away energy, and since energy is equivalent to mass, the black hole slowly loses mass over time. This radiation is extraordinarily faint. A black hole with the mass of our Sun would take about 10 to the 67th years to evaporate completely. Supermassive black holes at the centers of galaxies would persist even longer, perhaps 10 to the 100th years, a number called a googol. To put this in perspective, a googol is one followed by 100 zeros. It is larger than the number of atoms in the observable universe. The time for supermassive black holes to evaporate is one followed by 100 zeros years. These numbers exceed our ability to truly comprehend them. The largest black holes we know of have masses of tens of billions of solar masses. These monsters, found at the centers of the largest galaxies, would be the last significant objects in the universe. They would continue accreting whatever sparse matter drifted near them, growing slightly, while simultaneously losing mass to Hawking radiation. Eventually radiation would win, the black holes would shrink, evaporating faster as they became smaller, until they vanished in a final burst of gamma radiation. But even black holes will eventually fade to nothing. After the last black hole is evaporated, the universe will be a dilute soup of particles and radiation, spread thinner and thinner as expansion continues. The temperature will approach absolute zero. No work can be done, no structure can form, no process that we would recognize as physics can occur. This final state is called the heat death of the universe. It represents maximum entropy, complete equilibrium, the end of change. The heat death is not a dramatic explosion or collapse. It is the opposite, an endless fading into darkness. The universe does not die with a bang, it dies with a whisper that stretches across eternity. Some cosmologists have considered even more exotic possibilities, though these remain highly speculative. If dark energy strengthens over time, a scenario called phantom dark energy, the acceleration could theoretically become so extreme that it tears apart everything in the universe. First galaxies would be ripped apart, then stars, then planets, then atoms themselves. This hypothetical big rip would occur in finite time, perhaps 20 or 30 billion years from now, depending on the assumed properties of dark energy. All of space-time would be destroyed as this expansion reached infinite velocity at every point simultaneously. However, this scenario requires dark energy to behave in ways that current physics finds difficult to explain, and most cosmologists consider it unlikely. Current observations do not favour the Big Rip scenario. The data is consistent with dark energy being a cosmological constant that does not change over time, but we cannot rule it out completely. The nature of dark energy remains mysterious, and surprises may await us. Some physicists have speculated about even more distant futures, though these ideas venture far beyond established physics into the realm of theoretical possibility. Random quantum fluctuations could, in principle, spontaneously generate new particles, new atoms, even new structures over timescales of 10 to the 10 to the 50 years. Some calculations, extrapolating quantum mechanics to scales where our understanding grows uncertain, suggest that random fluctuations could produce entirely new universes, Big Bangs emerging spontaneously from the quantum vacuum. But these timescales are so vast that they lose all practical meaning. They exceed the number of particles in the observable universe. They exceed the number of possible ways to arrange those particles. They represent durations that no entity could ever experience, and our confidence in predictions at such scales is correspondingly low. The expansion of the universe is not just a fact about astronomy, it is a fact about the nature of existence itself. We live in a cosmos with a beginning. Approximately 13.8 billion years ago, space and time emerged from conditions we do not fully understand, and everything we see and everything we are traces back to that origin. The atoms in your body were forged in stars that themselves formed from primordial hydrogen created in the first minutes after the Big Bang. You're made of material that has been part of this expanding universe since its earliest moments. The carbon in your cells was fused in the core of a star that lived and died before our sun existed. The iron in your blood comes from supernova explosions that scattered heavy elements across space billions of years ago. The gold in jewellery traces back to neutron star collisions, among the most violent events in the universe besides the Big Bang itself. Every complex atom in your body has a history stretching back billions of years through stellar cores and interstellar space, all ultimately deriving from the simple hydrogen that emerged from the first moments of creation. We live in a cosmos that is growing, not into something, but within itself. Every day, more space exists than existed the day before. The distances between galaxy clusters increase. The universe becomes, in some sense, more. This is not growth in the familiar sense of a tree adding leaves or a city adding buildings. It is the fabric of reality itself stretching, creating more of itself. The rate of this growth is accelerating. Whatever dark energy is, it is winning the long battle against gravity. In the deep future, acceleration will isolate islands of matter from each other until observers can only see their own galactic neighbourhood. The cosmic horizon will shrink, hiding the evidence for the Big Bang and the existence of other galaxies. The universe will become lonely, then cold, then dark. The acceleration of cosmic expansion is perhaps the most unexpected discovery in the history of cosmology. When scientists first measured the expansion rate in the late 20th century, they expected to find it slowing down. Gravity, after all, should be acting as a brake. The mutual attraction of all the matter in the universe should be decelerating the cosmic expansion, even if it could never stop it entirely. What they found instead was acceleration. Something was pushing the universe apart faster and faster. That something, whatever it turns out to be, now dominates cosmic evolution. We live in a cosmos dominated by forces we do not understand. Dark energy, making up more than 2/3 of everything that exists, remains almost completely mysterious. Dark matter, comprising most of the rest, is only slightly less opaque. The matter we know and understand, the atoms and molecules and particles that make up stars and planets and people, is a tiny fraction of the whole. We are foam on an ocean we cannot fathom. This is a remarkable situation for any species to find itself in. After thousands of years of intellectual progress, after developing mathematics and physics and chemistry and biology, after sending probes to other planets and detecting gravitational waves from colliding black holes, we find ourselves unable to explain what most of the universe is. Humility is appropriate here. The universe is not obligated to be comprehensible, and we are fortunate that it is as comprehensible as it is. We live in a cosmos facing a crisis. Our best measurements disagree. Our standard model may be incomplete. The Hubble tension points to physics beyond what we currently know, waiting to be discovered. This is not a failure of science. It is science working exactly as it should, revealing the boundaries of our knowledge and pointing toward new frontiers. The tension between local and early universe measurements of cosmic expansion is not a minor discrepancy to be swept under the rug. It is a signal, possibly the most important signal in cosmology today, that something is missing from our understanding. Either we are making measurement errors that no one has been able to identify, or the universe works in ways we have not yet grasped. The history of physics is filled with moments when small discrepancies led to revolutionary discoveries. The anomalous precession of Mercury's orbit, a tiny deviation from Newtonian predictions, was ultimately explained by Einstein's general relativity. The ultraviolet catastrophe in blackbody radiation led to quantum mechanics. The perihelion advance of Uranus led to the discovery of Neptune. The Hubble tension could be another such moment, a crack in our current understanding through which entirely new physics might be glimpsed. We live in a cosmos with a fate. If current understanding holds, the far future is cold and dark and empty, but that fate is billions and trillions and googles of years away. On human timescales, on biological timescales, even on geological timescales, the universe changes imperceptibly slowly. We have time to learn, to explore, to wonder. The timescales involved are worth contemplating because they reveal how brief our cosmic moment truly is. The universe has existed for 13.8 billion years. Our sun will last another 5 billion years before expanding into a red giant and eventually becoming a white dwarf. The last red dwarf stars will burn for perhaps 10 trillion years. Black holes will evaporate over timescales of 10 to the 100th years. Against this backdrop, the few thousand years of human civilization are barely a blink. The few 100,000 years of human existence are less than a heartbeat. Yet in that brief moment, we have learned the age and fate of the cosmos. We have detected light from 13 billion years ago. We have mapped the structure of the universe across billions of light years. We have discovered that space itself is expanding and that the expansion is accelerating. This knowledge is precious precisely because it is improbable. Most matter in the universe will never contemplate its own existence. Stars burn and die without knowing they are stars. Planets orbit without understanding orbits. Galaxies collide without experiencing collision. But here on Earth, matter has organized itself into creatures that can understand these processes, that can trace their own origins back to the Big Bang, that can predict their own cosmic future. This is remarkable. This is, as far as we know, rare. The question of what the universe is expanding into has a strange answer: nothing. There is no void outside the cosmos waiting to be filled. There is no container being enlarged. There is no edge being pushed. The universe contains all of space, and space is simply becoming more. This answer is difficult to accept because it contradicts every intuition we have developed through everyday experience. But the universe is not obligated to conform to human intuition. It operates according to laws that we discovered through careful observation and mathematical reasoning, not through common sense. The expansion of space, the acceleration driven by dark energy, the cosmic web of structure, the fate of heat-death. All of these emerge from physical principles that transcend our daily experience. The fact that we can understand these principles at all is itself remarkable. Why should the universe be comprehensible to creatures evolved for survival in African savannas? Why should mathematics, developed for counting and commerce, describe the behavior of subatomic particles and the expansion of space-time? Why should the same laws of physics apply here and in galaxies billions of light years away? These questions have no obvious answers. The universe could have been chaotic, random, incomprehensible. Instead, it follows patterns that human minds can grasp. This is not guaranteed, it is a gift. Consider again the balloon analogy, despite its limitations. Imagine you are a two-dimensional creature living on the surface of a balloon. Your entire reality is the two-dimensional surface. You cannot perceive the third dimension in which the balloon exists. Now imagine the balloon inflates. Every point on the surface moves away from every other point. You and your neighbours all recede from each other, but you are not moving on the surface. The surface itself is expanding. There is nowhere on the surface that is the centre of the expansion. Every point seems to be at the centre from its own perspective. And if you ask what the balloon is expanding into, the question assumes access to the third dimension that your two-dimensional perception cannot grasp. Now, add a dimension and apply this to our universe. We are three-dimensional creatures perceiving three-dimensional space. If our space is the surface of some higher dimensional structure expanding in a fourth spatial dimension, we cannot perceive that higher dimension directly. Questions about what space is expanding into become as meaningless to us as questions about what the balloon surface is expanding into would be to a creature confined to that surface. This may not be a fully satisfying answer. Human minds did not evolve to contemplate the geometry of space-time. We evolved to find food, avoid predators, and navigate the African savanna. The intuitions that served our ancestors well are not designed to comprehend cosmic expansion. Yet somehow, through mathematics and observation, we have managed to understand things that our ancestors could not have conceived. Understanding cosmic expansion requires setting aside our evolved intuitions and accepting that reality at its largest scales is profoundly different from reality at the scales we inhabit. We are creatures of a particular size, living on a particular planet for a particular duration. The universe is vaster and stranger than our ancestors ever imagined, and yet we can understand it. Through telescopes and satellites and mathematical models, through painstaking observation and creative theorizing, we have learned truths about the cosmos that our great-grandparents could not have dreamed. We know the universe is expanding, we know it is accelerating, we know it had a beginning and will have an end. We know we are made of matter forged in stars that lived and died before our solar system formed. This knowledge is hard-won and precious. It represents one of humanity's greatest achievements, and it remains incomplete. The Hubble tension tells us something is missing. Dark energy tells us most of reality remains hidden. The nature of time before the Big Bang, if the concept of before even applies, remains utterly unknown. There is so much more to learn. The universe continues expanding, indifferent to whether we understand it or not. Space grows between the galaxies. Dark energy accelerates the separation. Stars are born and die, structures form and dissolve, the cosmic web stretches ever thinner. The expansion rate is not just a number, it encodes the fate of everything. A slightly different Hubble constant would mean a different cosmic age, a different balance between matter and energy, a different ultimate destiny. The precision measurements cosmologists chase are not academic exercises, they are attempts to read the universe's future in its present behaviour. Future missions will continue this quest. The Nancy Grace Roman Space Telescope will survey wide swathes of the sky for distant supernovae, providing new constraints on dark energy's properties. The Vera Rubin Observatory in Chile will catalogue billions of galaxies, mapping cosmic structure across vast volumes. The Euclid satellite is already at work measuring how galaxy shapes are distorted by intervening dark matter, probing the geometry of space-time itself. The next decade promises revolutionary advances in our understanding of cosmic expansion. The James Webb Space Telescope is already observing the most distant galaxies ever seen, pushing our view back to when the universe was only a few 100 million years old. Ground-based observatories with adaptive optic systems can now image with clarity rivaling space telescopes. Gravitational wave detectors are opening an entirely new window on the cosmos, detecting the ripples in space-time produced by merging black holes and neutron stars. Each new instrument, each new technique, brings fresh data that tests our theories and often surprises us. The convergence of multiple observational methods is particularly powerful. When different approaches to measuring cosmic expansion agree, we gain confidence in our understanding. When they disagree, as with the Hubble tension, we know something interesting is happening. Either we are making subtle errors, or the universe is telling us something new. History suggests that unexpected tensions often lead to breakthroughs. These observations may resolve the Hubble tension, revealing whether the discrepancy stems from measurement errors, unusual local conditions, or genuinely new physics. They may reveal that dark energy evolves over time, fundamentally altering our predictions for cosmic fate. They may uncover surprises we cannot yet anticipate. The universe has proven again and again that it is stranger than our theories predict. The possibility of new physics is thrilling. For the past 50 years, the Standard Model of Particle Physics and the Lambda CDM model of cosmology have explained observations with remarkable success, but we know both models are incomplete. The Standard Model does not include gravity. lambda CDM does not explain what dark matter and dark energy actually are. Both models have parameters that must be measured rather than derived from deeper principles. A fundamental theory that explains these parameters, that unifies gravity with quantum mechanics, that reveals the true nature of dark energy, would be a crowning achievement of human intellect. Such a theory may emerge from the puzzles we are now confronting. The Hubble tension, the unexplained value of the cosmological constant, the nature of dark matter, the origin of cosmic inflation. Each represents a crack where new physics might break through. Future generations of scientists will look back at our era as a time when these puzzles were first clearly articulated, when the data became precise enough to reveal tensions that less accurate measurements had missed. And here we are, on this small planet orbiting an ordinary star in an ordinary galaxy, looking out at all of it and asking questions. That alone is remarkable, that we can ask what the universe is expanding into and understand that the answer is nothing, and be troubled and amazed and humbled by that answer. This is what it means to be conscious beings in an expanding cosmos. Our planet is an insignificant mote in the vastness of space. Our sun is one of hundreds of billions of stars in the Milky Way, which itself is one of hundreds of billions of galaxies in the observable universe. The light we see from distant quasars left on its journey when the universe was young, billions of years before Earth existed. The universe was ancient before our solar system formed, and will persist for eons after our sun has died. This cosmic perspective has practical implications for how we think about ourselves and our world. If the universe is vast and mostly empty, if Earth is a small planet orbiting an ordinary star, if human civilization is a brief flicker in cosmic time, then perhaps we should treat our existence with greater care. We know of no other place in the universe where life has arisen. We know of no other species that can contemplate cosmic expansion and the heat death of the universe. These realizations impose a kind of responsibility. To preserve the only world we know supports life, to extend our understanding as far as we can, to pass on what we have learned to future generations who may carry this knowledge forward even after we are gone. The search for extraterrestrial life gains new significance in this context. If the universe is expanding and will eventually become cold and dark, the window during which life can exist is finite. We are in the early stages of that window, when stars still form and shine, when energy is still available to power biological processes. If other intelligent life exists, it too is embedded in this expanding cosmos, facing the same ultimate fate. The search for signals from other civilizations is not just scientific curiosity, it is a search for cosmic companions in a universe that may eventually leave all life isolated and alone. The expansion of the universe also raises deep questions about the nature of reality itself. Why do the laws of physics allow for cosmic expansion? Why do they permit the formation of stars and galaxies and life? Why is there something rather than nothing? These questions may forever exceed our ability to answer. But the fact that we can ask them, that the universe has produced creatures curious about their own existence, suggests that consciousness is not an accident, but a possibility woven into the fabric of reality. Philosophers call this observation the anthropic principle. In its weak form, it merely notes that any universe we observe must have properties compatible with our existence. We could not find ourselves in a universe that did not allow conscious observers. In its strong form, it suggests that the laws of physics may somehow require the eventual emergence of observers. This remains deeply controversial. Most scientists prefer explanations that do not invoke consciousness as a cosmic necessity. But the question persists. Why is the universe comprehensible? Why are its laws mathematical? Why does it contain observers at all? We may never know the answers, but the questions themselves are precious. They emerge from the same cosmic expansion we seek to understand. They are possible only because the universe has evolved for billions of years, because stars have forged heavy elements, because planets have formed inhabitable zones, because evolution has produced brains capable of abstract thought. Every question about the cosmos is itself a cosmic phenomenon, arising from the very processes it seeks to explain. The journey from Hubble's first measurements in 1929 to today's precision cosmology spans less than a century. In that time, we have learned that the universe began in a hot Big Bang, that it is expanding, that the expansion is accelerating, that most of the cosmos consists of dark matter and dark energy we do not understand. We have mapped the cosmic microwave background. discovered the cosmic web, measured the age of the universe to within about 38 million years. We have learned more about the cosmos in this brief period than in all of prior human history combined. Yet we have also learned how much we do not know. The universe continues to surprise us, and that capacity for surprise is perhaps its greatest gift. This is not cause for despair, it is cause for wonder. The same processes that created galaxies and stars also created planets, and on at least one planet, created life. The atoms forged in stellar explosions billions of years ago now contemplate their own origins. The universe has become conscious of itself through beings like us. That consciousness, however brief in cosmic terms, has value beyond measure. Yet in this insignificant corner of an unremarkable galaxy, matter organized itself into complexity sufficient to contemplate its own origins. Atoms assembled into molecules, molecules into cells, cells into creatures, creatures into societies that build telescopes and satellites and mathematical theories. The universe produced beings capable of understanding that it is expanding, that it had a beginning, that it will have an end. This is as close to magic as physical reality allows. The universe is not expanding into a void. The universe is the void becoming something else. Space emerges where none was before. Time flows from a moment when time itself began. Reality unfolds according to laws we are still discovering. The expansion of the universe is the expansion of possibility itself. Every new moment creates more room for matter and energy to arrange themselves, more room for complexity to emerge, more room for stars and planets and perhaps minds to exist. We ride this wave of expanding space embedded in its fabric, carried along by the growth of reality. Someday, unimaginably far in the future, expansion will win completely. The universe will be cold and dark and empty. But that day is not today. Today stars still shine, planets still orbit, and conscious beings still wonder about their place in the cosmos. Today the universe is young and rich with possibility. If this story has changed how you see the night sky, hit that like button and subscribe. The cosmos has more secrets to reveal, and we are only beginning to understand them. Each observation brings new questions. Each answer reveals deeper mysteries. The expansion of the universe is not just something that happened. It is happening now in this moment, creating more space between the galaxies, even as you read these words. We are part of a universe in motion, a cosmos in transformation, a reality that refuses to stand still.